Sir, Arijit sir?
Hello, am I audible?
Yes, sir.
Hello.
Yes, sir. Very good evening, sir.
Yeah, okay. Very good evening.
Yes, sir. Participants are joining, sir. Just we will wait for a few minutes, then we will start the session, sir.
Okay, no problem.
Yes. Sir, okay, sir. We'll start the session, sir. So, a very good evening to everyone. We,
Okay.
wa- we are truly honored to welcome today's first speaker, Dr. Arijit Karati, sir, to the day 5 of the AICTE sponsored Faculty Development Program on Joy of AI in Action, applying traditional and agentic AI to real world problems, scheduled to be held online from August 18th to August 23rd, 2025. Arijit Karate sir received his PhD degree from IIT Dhanbad in 2018. He was a postdoctoral researcher in the Department of Computer Science and Engineering (CSE) at National Sun Yat-sen University, Taiwan from 2018 to 2020. Currently, he is working as an associate professor in the Department of CSE at NCSU, Taiwan, where he supervises the Cryptology and Network Security Lab. He was the recipient of the 2019 Postdoctoral Researcher Academic Research Award and part of the 2023 Future Tech Award from the National Science and Technology Council (NSTC) of Taiwan. He has also received the Excellent Faculty Award in Academic Research at NCSU in 2024. His research areas include applied cryptology, security, and decentralized data privacy. He is a professional member of the ACM and a senior member of IEEE. Thank you, sir, for joining our today's program. Over to you, sir.
Thank you for a nice introduction. So let me share my screen. Okay, so my slides are visible?
Yes, sir.
Okay, thank you. Okay, so good day, everyone, and thank you very much for having me. So I'd like to thank the organizing team members for this FDP program, and they are so kind to invite me. And well, so this talk we are going to discuss about deconstructing the dark side, emerging security risk in AI. So in this talk, mainly we are not focusing about how good AI is or could be, or what are the techniques to detect something or to solve some problem. But the opposite side will be our main focus for today's discussions. So AI is now an integral part of our daily life. Most of us, we know, we use many apps, we use many online website to solve our problem. Sometimes students also use some AI tools to submit some assignment as well, right? So yeah, so AI has good and bad both sides. So it influenced a lot to us in different segments such as shopping. It could be communications, medical diagnosis, urban navigations, etc. So it is also transforming our industries day by day rapidly, expanding the capabilities what we have never seen before, and altering the security paradigms. As AI systems advance in autonomy, intelligence, and integrations, the primary concern shifts from AI's capability to its security right now, or like recent days. So in this new era, security is not bounded or not just about the firewall, like just to what is it, just to check that incoming and outgoing packets. It's nothing like that. It is more beyond than typical firewalls that what we have seen in past 20 years. So it's about the foresight. So here is my outline for today's talk. Like first, I briefly discuss about us, like what we do or what kind of research focus we have right now in our current labs. Then I'll be discussing about cybersecurity in recent days, the dual nature of AI, categories of AI security, followed by mitigation strategies, briefly some terminologies. Then I'll be discussing about federated learning and briefly introduce one of our solutions that is based on federated learning to resist the backdoor attacks. And finally, some key takeaways. Okay, so in Taiwan, as like in India, we know like we have like in India, we have like DST, right? So here we have like NSTC, National Science and Technology Council. So in this national science NSTC, we do have several fields for research projects or some kind of research advancements. However, Taiwan government has designated cybersecurity is one national security as a major national policy to establish a secure environment for developing a smart nations. And to incorporate or to reach the goals, NHTC has introduced one national level cybersecurity center, research center, which is known as Taiwan Academic Cybersecurity Center. Okay, yeah. So it is known as Taiwan Academic Cybersecurity Center, which is also known as TACC. So in these cybersecurity centers, they focus on recent cutting edge technologies uh, in security fields, and they are trying to integrate more countries to uh, develop some modern technologies collectively, and try to provide some kind of security solutions as service. So currently this TSCC, this research center actually list out 9 universities um, collectively to do work, research work under this TSCC umbrella. And these are the 9 universities, and this is our university, National Sun Eastern University. In this National Sun Eastern University, we do have some research center which is known as Information Security Research Center. This research center is affiliated under TSCC and followed by like NHTC. Yeah. So in this research center, there are 11 faculties. These faculties and which is led by Professor Fanchini. He is the center director. So in this research center, we do have multiple research focus. For example, like post-quantum cryptography, artificial intelligence security, as well as zero trust architecture like ZTA, and also some network level security measurements. So some professors are having with different research focus. So for example, my main research focus is post quantum cryptography or like applied cryptography. However, also I do have some research interest on AI part, so I'll be happy to share some of my recent studies, although I'm not so expert in AI security. Yeah, so yeah, anyway, so that's a brief introduction about like our research center and what we do in this particular research center. Now coming to the main topic today. So as we know, like AI is a very common term. Even child, many kids also, even though they don't know the impact of AI, they also know the term AI, or they use some of those technologies knowingly or unknowingly, right? So yeah, so in recent years, what we have seen, like AI is actually growing. AI means AI market is growing rapidly. So the AI in the security market is expected to grow significantly from 27.6 in this current year, right? 27.6 billion in 2025 to around 70.1 by billion USD billion by 2030, at a CAGR of 20.5%, which is even very attractive number, right? And this result actually tells us the growth or the future potential of AI technologies for our societies. It could be like any smart development in future, maybe may consider like some AI techniques to solve from zero, not from zero, you can consider like from 1 to 100, any kind of problems maybe they can solve. So it is a little bit futuristic concept. However, their technologies is growing at this moment, so it's not like fully mature technology. So by 2033, it is expected that market size will be around USD 123 billion, which is a quite handsome amount. So yeah, so this is some kind of data I received from online. So basically this growth is driven by increasing volume of cyber threat, necessitating AI for anomaly detections, like misbehavior detections, automated something like automated responses, or even like adaptation to new attack pattern. And this growth is not only talks about the good thing of AI. Sometimes it is also possible to provide some security solutions, or due to the bad side also, many people thinks that there should be some security requirements. So due to the emergence of generative AI, like their growth, it is also very natural that there are many more um, attentions towards how to find out the vulnerabilities inside AI. That is the prime focus for the hackers nowadays. Okay, so for example, like prompt injections or data poisoning. So these are very common attack type that can be found in AI domain, or AI based like trained model inside that. Well, so there are many players are there which are currently working on AI or related to AI's growth, and some of them I have mentioned some of them. Right, for example, like Samsung right now is very popular in generative AI. So most of us we know like mobile phone or something like we do have many different use cases nowadays due to AI era, right, which is done by Samsung. Nonetheless, Amazon, AWS, Microsoft, Nvidia is also a very popular company, is known for this AI growth. Um, IBM, Google, Cisco is also there. These are mainly the key player for this technological growth in AI, not the uses of AI. So they are working behind the scene. They are working to develop some kind of AI algorithms to provide some services, not using services. Okay, so there are many more. So these enterprises are adopting AI native security frameworks, integrating machine learning for threat detections, and deploying autonomous agents. And this kind of autonomous agent nowadays again is a very popular terminologies. Those agents are helping the system to resist against some attacks. Okay, so few of those attacks we'll discuss after some time. Okay, so cloud-based and hybrid deployments are also increasing nowadays. Now, if we see in terms of the globe's point of view, there are different kind of areas like Europe area, APSC, like Asia Pacific, MEA, Latin America, and North America. So mostly it is expected that North America will hold the largest global AI in security market share due to their many cutting edge technologies, as well as some popular companies like global companies. So here you can see I just copy those data. So here you can find out that their market growth, not growth, like market cap is like 7.14 billion USD for this. So anyway, so here what we can find out that this figure actually tells us that what kind of services or what kind of technique we are using in AI in recent years, or will be using in couple of years from now, maybe 5 years from now. So mostly people are talking about the machine learning part of AI, and they are working mainly inside the advancement of some machine learning techniques, for example deep learning, federated learning, and so on. And there are also potential growth in context aware computing, which is also comes under this AI segments, as well as the NLP. So it is possible that many people are talking about machine learning, and here you can see the number is showing like it is more than 50% of the total weightage, they are being used, or the researchers are being focusing on machine learning improvement or their technique improvement. So despite the 93% of security professionals believing AI enhances cyber security, however, 77% of organizations feel unprepared for AI-driven threats. The reason why most of the companies, they're talking about AIs, but they are not fully using AI features in their core internal systems due to the potential security breach. So they are also not sure, or they are actually trying to design some models which can provide security. So 77% organizations they think they're not prepared for AI driven threats, highlighting a critical risk gap. So as we see, like, AI transforms industries, cybersecurity must evolve to ensure safe AI, and this is the today's discussions. So, as we stand on the edge of an AI powered future, it is easy to get swept up in the excitement, mainly in automations, personalizations, or even breakthroughs in medicines. Like most of happy market you can consider, it is like hospitals, and most of people are talking about autonomous machine which can actually check patients, or they can actually perform surgery. However, we are not still so sure that can we trust those machines or not, right? So yeah, anyway, so those are the uh, power of AI as of today we know. But today I want to shift our focus to the shadow that comes within with this actually light or behind the scene. So AI nowadays is not just a tool; it is a like a force multiplier. And like any powerful tool, it can be misused, it can be misunderstood, or even we can use AI as weapon. Now, how we can consider this as weapon kind of things, that also will I'll briefly sorry I'll briefly highlight later. So it is possible that from subtle biases in algorithms to full-blown adversarial attacks, the risks are real, and they are growing, and they are growing very first, actually. And this talk is about peeling back the layers, deconstructing the dark side of AI, and we'll try to explore what threats are emerging and why those are critical to be considered. So, if AI is going to shape our future, then securing it must be a part of the blueprint. So, let's dive in what they really means. So the first part is the dual nature of AI. Most of us, we already aware of this factor. So let's begin by acknowledging a fundamental truth. AI is neither inherently good or bad, like nor bad. So it's dual nature. So on the one hand, it is actually transforming the industries, revolutionize all everything, enhancing the productivity and solving the problem very fast manner, which we never thought before, that without AI we thought like we never can solve with that much fast or with that much efficiency. On the other hand, it is also introducing new vulnerabilities and amplifying the existing ones. Why it is so? Because nowadays, due to this AI, due to the AI systems, as we know, AI is nothing but many checking and learning things based on existing things, right? So it is possible that if we have trained our model so well from the attacker's point of view, then it is possible that attacker's model can predict what is the underlying security of a certain systems. Or even it is possible attacker can actually inject some not fake data, I would say, like a misleading data into a training model, for example, during training, which actually leads to some vulnerable global model. It is also possible. So thinking of I would say that AI like a fire. So it can warm your home during winter, as well as it can also burn it down. So it's all depend on how you use it, how much you are controlling that AI in your daily life or in your systems. Sorry, sorry. Okay, so the same algorithm that helps to detect cancer can also be repurposed to generate defects. And that is very interesting. The chatbot that offers mental health support kind of things, they can be also manipulated with misinformation. So what I'm trying to say, that AI is nothing but some kind of executions of certain algorithms, and those algorithms can be used for good purposes, it can be used for bad purposes. So what we need to do is, that is, we have to make our policy more strong, rigorous, in such a way that we can minimize the bad side of AI. So this duality is not just philosophical, it is actually practical. It means that every advancement in AI must be accompanied by conversations about like ethics, that is what we said, safety, these things, ethics, safety, and control. If we ignore the darker potential, we risk building systems that are powerful but dangerously unchecked. So what I'm trying to say, although it is like, we are very happy to welcome those systems, because they can solve our day-to-day problems, or even they can solve, for example, some mathematical problems, even they can solve, or even they can do certain amount of task way more faster than a human being. However, on the other hand side, if we don't follow certain ethics, safety, and control, these are the three principles, then it could have some dangerous sides also, which we may overlook. Now that we have acknowledged actually AI's dual nature, now if we zoom in a little bit more on some specific threats that we are going to find out on the surface, then we can find out that these are not like just theoretical risk. They are already being exploited in the wild. So here I have listed some of like some like a few types, like categories of AI security. So first we have adversarial attacks, where malicious actors certainly manipulate input data to fool AI models. What does it mean? It means that a few pixels changed in an image, it is possible that suddenly a self-driven car or autonomous car mistake a stop sign for a speed limit sign. So adversarial attack is something like you are fooling the models with some manipulated input. And this manipulated input eventually lead to have one erroneous global model. Then there is another one which is known as data poisoning. And in this data poisoning, attackers corrupt the training data itself. Imagine like feeding biased or misleading data into a model. So it's like a teacher child model. For example, like like you are teaching a child with an equipped textbooks. What will be the result? The result will be skewed decisions. It could be flawed predictions, or even dangerous outcomes. So we can consider, for example, I am reading, so that is what I just try to emphasize, from where we are actually learning some correct training based on some data. If there is something wrong in that particular during the training phase, it will eventually make everything wrong in terms of decisions. So that being said, like data poisoning, it is something like a very serious um, consequences at this moment. Like how we can mm, how we can actually resist, or how we can evade this data poisoning from that occurs. We also face threat from model inversions as well as membership inference. So these techniques that allows attackers to extract sensitive information from from trained model. So it is possible that you are actually sharing your local model with the server, and server is actually aggregating everyone's model to reach a global standard robust model. However, during this transmission, it is possible that attacker can extract some sensitive information. In other words, your AI might be leaking some private data without even realizing it. So how to provide certain robust model against model inversion or membership inference? the, ne- the next one is the privacy violations, similarly, like revealing like sensitive user data, autonomous weaponizations, like AI in military or surveillance. So surveillance, why I'm trying to say here, like it is something like, for example, you are actually monitoring some kind of restricted areas with some security cameras. So but when you are actually sharing those information and you are training the model for some autonomous activity, to impose some autonomous activities, and during that I am feeding with some wrong information or some kind of wrong picture, due to that it is possible that you actually can evade the whole systems. Okay, so these vectors, whatever we have seen right now, adversarial attacks like data poisoning, model theft, privacy violations, and so on. So these vectors are actually evolving very fast, and we are not very much focusing on those such kind of issues. And as AI systems become more integrated into some critical infrastructure or even backend also, or the core network, the stake gets even higher. So understanding these traits is the first step towards building resilient and trustworthy AI, which is actually the prime concerns from many countries or the governmental government services, like those services which is actually coupled with some AI decisions. Okay, so now let's move from like a theory to reality. So AI related security breaches, like security breaches, like we can say, are not just hypothetical. They have already happened, and they are shaping how we think about that risk. One very notable example is the use of deepfake technology in political, for example, disinformation campaign. So this synthetic video have been used to impersonate, maybe like consider one public figure, and spread some false narratives and manipulate public's opinion during voting or during elections. So it is very much like concern aspects. Another case, for example, like we can consider, like another case involves like adversarial attacks on image recognition systems. Researchers have shown that by subtly altering images, they can trick AI into misclassifying objects, like like uh, like identifying a turtle with a rifle, for example. Okay, so the thing is that we are not changing the image, or for example, so what I'm trying to tell you here, for example, some automated systems which can trigger certain actions based on some results, for example, and that result should come as turtle, for example, but somehow that machine detects that turtle as rifle. Now imagine the implication of that kind of situations in military or surveillance context. So that is actually the dual nature of AI, how we are going to use in our day-to-day life. We have also seen some AI chatbot that exploit to generate some harmful contents or leak some sensitive information during chatting with AI chatbot kind of things. In one instance, like we can consider, like user were able to coax a chatbot into revealing some proprietary information by crafting some kind of clever prompt. So the chatbot is actually interacting with the user, but in such a way that user there is a high chance that user will actually provide more information unknowingly, which is not actually like is required. So these are not similarly, there are some kind of other aspects like Tesla autopilot misreading adversarial road sign. So it is a couple of news were there in recent days, right? So like healthcare bias due to skewed data, improper data. So data is actually the power nowadays. And most of, for example, like Google, for example, Google has lots of data to feed. So that could be one of the reasons that Google AI is also a very industry standard or some kind of a leading positions. They're holding a leading positions in AI advancement. So nowadays we are only focusing on data. Which companies or whichever the industries, they have lots of user data, they are rich actually, because they can control the whole societies in the near future. Yes. So whatever the consequences or whatever the issues that we have just briefly discussed here, that is actually, they are not isolated incidents. They are the signals. The signal that AI systems, if left unguarded or some kind of unchecked, it can be turned against us, against human. And by studying these cases, we gain insight into how vulnerabilities manifest and how we might prevent them. Okay, so coming to the next part, that is now we have seen how AI can be attacked or it can be misused. Now let's talk about the uphill battles of securing it. Unlike the traditional softwares, AI systems are, I would say, like it's dynamic, right? Why it is dynamic? Because they can learn, they can adapt, even they can evolve, and that makes them harder to lock down. So the first issue here, one major challenge is opacity. Many AI models, especially deep learning systems, operate as black boxes. What does it mean? We know what goes in, we know what comes out, but we may not know always why or how they are actually calculating. This lack of transparencies makes it difficult to detect when something goes wrong or when a model has been compromised. The next one is this one, data dependency. Because AI is all about data dependency based on the data. AI is only as good as the data is trained on. If your data is high quality, if data is actually untempered, then your result will come good. If the data is biased, for example, or if the data is incomplete, or if such data maliciously altered, then what will happen? The model inherits those flaws, and once it is deployed, retraining or correcting these models is not so easy. It's not so straightforward. So data dependency is a high concern. The data dependency is not the issue. The issue is like the quality of the data, because there is a dependency on data, right, on behalf of AI. The next one is scalability issue. So just now we have said the data dependency, right? Now the next one is little bit more extended format, um, like data here, like some scalability issues, because we have seen in past like past few years that scalability is a prime concern, one of the prime concerns. So securing one model is like it can be considered as hard enough, right? Because of this data, as we just now we have seen. Now consider securing thousand across different platforms, different use cases, or even different environments. That's a whole other level of complexity. So it is, I would say, it is a sword, is a very sharp sword. So you have to handle very carefully. And finally, there is a challenge of regulatory lag. Here the technology is running ahead, while policy and governance are still tying their shoes. Because what happens, the government and the companies, they should work together to maintain the space, speed or the pace. However, it is possible that companies are moving so drastically or rapidly. However, government is not catching. Now government means in terms of the regulatory, like in terms of the regulations, in terms of that policy making and everything, right? So without clear standards and accountability, accountability, that industries are left to navigate this kind of risk on their own, because they are actually moving fast. The regulatory, the policy making has not been finished, for example. So whatever the risk may come into this society, that will be fully responsible, those industries will be responsible for that. However, now think about for local or normal people, they are not aware of all those backend sides. If at any moment the data breach may come into the picture, then the company will be the sole responsible entities, which is actually um, very much critical for our advancements. Okay, so now coming to the next part, that is some mitigation strategies. Okay, so now that we have outlined some of the threats and some of those challenges, now let's talk about some solutions. So securing AI is not just about patching vulnerabilities. It's all about building resilience into the systems from day one. Why I said day one? Because we are actually dealing with data, right? So if we want to invoke some kind of security mechanisms, we have to start from very beginning, because once the data is compromised, after that, even though we provide some security mechanisms, the data has been compromised or that data has been lost. So there is no value of that. Okay, so there are some kind of mitigation strategies I tried to mention. First, we need robust model testing, which is very useful as one of the useful strategies. So before deployment, AI systems should be stress tested, like against some adversarial inputs, even edge cases, as well as some unexpected scenarios. That means before to deploy some kind of models or some kind of solutions which is based on some AI, we have to ensure that for all kind of situations it is working properly. Maybe why maybe most of us we already have seen. I will not ask name those companies, but some of those companies AI chatbot, they show some kind of inappropriate answers while the user asks for certain things. Okay, maybe in a bad manner ways. Okay, so those are something which is a loophole during robust model testing. Okay, so this kind of testing we can think as a digital fire drill kind of things, like preparing the model for worst case scenarios. The second one is data hygiene, which is very critical. As in the last slide I have just discussed, that is the data dependency. So data hygiene is very critical. Clean, diverse, and well curated training data may reduce the risk of bias and poisoning, means data biasness and data poisoning. And ongoing monitoring ensures that the data pipeline remains secure and it is trustworthy. And the third one is as an extensions of AI security, that is the explainability. So recall that I have said that black box technique. So we must embrace explainability. If we can't understand how a model reaches its conclusion or the output, we can't reliably audit or defend it. So techniques like SAP, so SAP is very popular technique, and LIME are helping open that black box, like revealing, try to explain like why certain kind of like outputs we reach to that kind of outputs. So those techniques actually help us to make AI decisions more transparent, more easily accessible for the end users. The next strategy is the access control, or you can consider like security aware design principles. So we need some robust, reliable access control and encryption mechanisms to protect models as well as datasets from unauthorized use. Very useful. And the last one is something regulatory frameworks and ethical oversight. So it is just talking about collaborations among different units. Now, units means I am actually talking about the researchers, I am talking about the policymakers, I am talking about the industry leaders. So these three entities, like industry, policymakers, researchers, they need to have some common collaborations, and that is the key to design strong regulations against the AI use cases. So security is not a solo mission, rather it is a shared responsibility. Okay. Now, as we wrap up, let's shift our gauge forward. So the road ahead is not just about patching the vulnerabilities or invoke some strong access control mechanisms or uh, the data. It's all about reimagining how we build AI from the ground up. Very like inspirational. So it's we have to actually think. So like it's not about how we are protecting against some specific attack, rather than we have to actually catch the types of attack. So maybe I fail to what is express my thought. So what I'm trying to say here, like, is something like there are many different kind of small problems. However, they may come together and can be categorized as a single group of attacks or types of attacks. So we have to reimagine and we have to build the trustworthy or resilient AI from that point of view. We need to embed security and ethics into the so-called DNA of AI development. That means like designing systems that are not only technically robust but also socially responsible. Very useful. So it's not enough for AI to be smart. However, it must be safe, fair, and accountable. That is what the society needs rather than the smartness we expect. So this requires a multi approach. Engineers, ethicists, policymakers, and customers like end users must collaborate. That is what I feel, to define what responsible AI looks like. We have to have some common understanding. We have to, or we need, a clear governance framework, auditing mechanisms, and transparency standards that evolve alongside the technology. And let's not forget educations. Building secure AI starts with cultivating a culture of awareness. So, training developers to think like defenders and users to questions what they see, or to ask themselves or ask yourself when you are the engineer or the developer, like what could be the misuses, or what could be the loopholes, or how it can be stretched in such a way that there could be some loopholes inside my training models. So the future of AI is not written yet, although there is a crazy hype, although there is a crazy hype of such kind of things, of AI recent days, at least past 2 3 years, but it is not fully functional at this moment. So we have still the opportunity and the responsibility, sorry, to shape it into something that empowers rather than endangers. And let's choose wisely. So that I hope will be our next move from the society's point of view. Okay, so most of time we got confused about these terminologies, although some AI experts maybe uh, some of the audience already know, but I just go through some basic stuff. So, for example, AI versus machine learning versus deep learning, these are the essentials nowadays, and they are the backbone of these recent AI technologies. So artificial intelligence is a science like mathematics or biology. It studies ways to build intelligent program, nothing else, or intelligent machines that can creatively solve some interesting problems. Why I'm saying interesting? Which is difficult for either, which is difficult for human to solve, or it takes much more time to solve. So those kind of problems, difficult or time efficient, these kind of things, if one machine can leads or achieve those features, then that can be part of this AI or this intelligent machines. Okay, so come to the next part, that is the machine learning. So machine learning is a subset of AI, that is artificial intelligence, that provides systems the ability to automatically learn and improve from experience without being explicitly programmed. What I'm what I what I I'm trying to say. So it is possible. So let's have some small example that I have one global model, and you are feeding me, you are sending your local model time to time. Based on that, I am adapting the situations and scenarios for which I did not write any code, means which kind of services or which kind of answers, for example. I don't have any ready-made answers. I did not feed such kind of direct answers to one chatbot. However, the chatbot communicating with many users try to find out the answers which it never eat or which is never feed. So that kind of features can be achieved with the help of machine learning advancements. So it's a technique through which, or some kind of algorithms are there through which we can solve the problem, and that problems was not defined before. It is a self-learning techniques. The next one is deep learning, or like deep neural learning also we can call. So it is a subset of machine learning which uses the neural networks to analyze different factors with a structure that is similar to human neural systems, similar to that. So that is deep learning. So if you see the picture, so it is much more clear. So here you can see that machine learning is a part of AI, and the deep learning is a part of machine learning as well as this AI, because this set is inside this. So this is as simple as that. However, we do have certain kind of algorithms already, but the question is that how safe those algorithms? Yes, those algorithms we can use to solve the problem, but how you can ensure, or how we can tell that attacker also not using the same algorithm to launch some attack? So this is the dual nature of AI. It is just a tool. It depends how we are using it, whether we are using as a good human's point of view or we are using the attacker's point of view. Okay, now next slide I'll be discussing about the federated learning, and briefly describe one of our recent works. So let's move on. So yeah, federated learning is a decentralized machine learning technique. It was initially introduced by Google in 2016, as I remember. So in FL, federated learning, data remains on local devices, and each participants, we technically call them as client. So each participants only upload locally trained model updates, such as like your model weights or model gradients, to the central server, and central server aggregates those local servers data using fed average algorithm like fed avg to update the global model. And this process is keeps on like repeating iteratively until the model converged. So this can improve, indeed, this can improve the performance of the global model, and it also increases the diversity of the training data. But federated learning have some problems, which actually like a prime concern for for us. The first one, not all clients are benign. So first of all, as we have just said that every clients, they will try to send their local training model, and those models will be aggregated as like fed average algorithm, and then the global model will be generated, and later those global model will be distributed. Now we can't con- consider or assume that all the clients are benign. Benign means like something like your trustworthy or some kind of genuine users. They will never betray their server or the services. However, in our recent or the real systems or environment, we can't assume all clients are benign. So the server did not know each received model weight is trained by what kind of data, because the server is only receiving the data from its client, okay, the training model. So it is possible that maybe some clients using some backdoor data sets to train their model and upload those bad model to the server, and server use those model during this like avg like average algorithm to generate the global model. And this is something like your backdoor attack. You are actually sending your bad local model, and the server is using that model to generate the global model. Since the bad information is already present in that particular like local model, the global model also should not be considered as attack free or uh, like a unbiased model. So that is the main problem in such kind of federated learning situations. It is also kind of a machine learning techniques. And the second one is the data, because in the federated learning there are two different types of data. The first one we call it as IID, and the second one we call it as non-IID. Okay, so here non-IID stands for non-independent and identically distributed data. This is a common in federated environment. Why? Because, for example, consider one systems you have developed where there is one server and there are multiple clients. You cannot assume that all clients, they are having with homogeneous training model or the data or the odd model weight. So in federated learning, non-IID model weights and bad model weights are there. All of these may damage the global model, whether it is bad model or some kind of different types of data. So how to effectively use the non-IID model? A model means, I mean to say model weight, and eliminate the impact of backdoor attacks or backdoor model of weight is a critical issue nowadays. Okay, so moving to the next type. So here I briefly discuss about the two different types of federated learning. So federated learning has two different types as far as I know. The first one is centralized and second one is the decentralized federated learning. In centralized FL, that is centralized federated learning systems, in these systems, each client will upload their model weight to a single server that we can see. Upload here, upload model weight to a single server and ask the server to train sorry, a global model, and then share that global model back to each client. Decentralized is little different. So decentralized means in that particular systems, each client will receive some model weight. For example, client 1 sending, so client 4 is receiving some model weight from client 1. Okay, so like this. So each client will get some model weight from another clients, and using their model. So for example, this is the client receive this client 1 model. Using this client 1's model weight, this client 4 will improve its own self model or the local model. So that is the principles of decentralized federated learning. So I'll be sharing with you one small piece of work. So in our testing, we have used centralized federated learning to test our systems or some algorithms, but it can be also used in decentralized federated learning. So I'll discuss at the time. So in these two types of federated learning, when addressing some model performance issues, it is often necessary to confront challenges such as the performance biasness caused by non-IID or model poisoning through backdoor attacks. So here what I have said, I have just said the training data model weight, how you are sharing in a centralized framework, in a decentralized framework. But both of these cases, data may be IID or non-IID. So these are the challenge, how to resist the backdoor attack in some extended scenarios where my data is heterogeneous, that means non-IID. So what is this non-IID is and why it is so much discussed? So here non-IID, because as I have said, like there are two different types of structure that or the distribution we can follow. That is the IID and non-IID. So non-IID stands for non-independent and identically distributed data. So in IID, each client is trained on data with same distribution. Now what do you mean by the same distributions? For example, like here if you look at this picture, so for example, like in MNIST data sets, each client is training data level 0 to 9, this one, that is independent and identically distributed. Everyone is following the same principles. Okay, everyone training their data based on some common principles. However, that is not the case for non-IID. In non-IID, each client is trained on data with different distributions. What does it mean here? It means, again, take the same picture here. For example, this person, client 1, for example, this is the client 1, training their model based on some labels, and that label is from, for example, like 0 to 2. Another client 2, for example, train labels 4 to 7 or 1 to 3 or 2 to 5, but not the same level as like the client 1 or the first client. So this is known as non-IID, and that is very much realistic in our society. You cannot believe that, although you have set some common principles, but you cannot expect that everyone is following the same principles and they're training their model based on the same train level 0 to 9. So it may keeps on changing. So some problem caused by this non-IID, and these are the three listed problems that we so far come to know. Decreased model performance. Here, clients lacking certain classes of data which may train bias models, or negatively affecting the global model's accuracy. Possible. The second problem could be unstable model aggregations. Here, here, what happens that when you are sending or like sharing your gradients with server, so gradient updates from different clients may point in conflicting directions, which may cause instability or like convergence issues, never converged in some standard algorithm like fed average, like yes, like fed average, FED, AVG. And the third one could be considered as like difficulties in model detections, also possible. Many existing methods, we have studied a couple of works where we have seen that some of those existing methods evaluate model quality based on the model similarity. But these approaches are only effective under IID conditions, not non-IID. So mostly they are considering everyone as their training level data is same, for example, 0 to 9. However, in real situations or the scenarios, data is mostly non-IID. Therefore, how to safely remove the impact of malicious weight while effectively leveraging this non-IID weight to improve model performance in a certain critical challenge we can consider. So to solve this kind of problem, we come up with some standard technique, which is known as attention mechanisms in knowledge distillations. So knowledge distillations involves utilizing a teacher model which possesses high accuracy to train a student model, okay, which lacks sufficient accuracy. So this process actually enhances the capability of student model. So it is a teacher student interaction kind of thing. Teacher will have a good attentions on the students so that student can improve their quality. So that is the basic idea. And in these methods, it can improve the student model's ability. Okay, so it can improve the student model's ability to achieve higher quality intermediate representations. It can also promote the student model to replicate the teacher's attentions distributions, which may facilitate that development of high discriminative features. And indeed, it can enhance its generalizations ability. So these mechanisms, as a part of the backdoor remove mechanisms, these are quite useful technique. So here I have mentioned two works, Lee et al.'s work and Zhang et al.'s work. So here also I give a basic idea of how they have used their technique to remove the backdoor attack. So Lee et al. Use a large amount of data to fine-tuning a teacher model and use such model to train poisoning students' model attentions. That is a quite remarkable ideas. However, it has little flaw. They use some large amount data, and we cannot expect that large amount data are always available in a good situations. The next one is Zhang et al. So Zhang et al. Proposed one work which is named as bad cleaner. This one, bad cleaner. So yeah, so bad cleaner, and this scheme use the attention mechanisms of multiple teacher rather than a single teacher to train poison student, poised like that kind of model student. However, without having any screening attentions. This is quite noticeable because they did not manage teachers' attentions, rather than they are directly using those attentions to training student model. And this will cause the students to learn wrong attentions if teacher has poor attentions, because these kind of distillations actually avoid or remove the backdoors based on the attentions, and that is why the name is attentions mechanisms. If teacher's attentions level or some kind of ranking or the value is poor, then the student will get some enhancement. However, their attention's value will get wrong, not accurate. Okay, so in this field, actually, we have one work, and that work is basically talking about backdoor defense technologies in non-IID federated learning settings. So this work is actually was done actually by my one master student, and this is also actually approved in one conference proceedings, IEEE conference on communications and network security, which is widely known as CNS, IEEE CNS. So it is not appeared yet, so to be appeared. So I briefly describe about the contributions. So in this work, we have three contributions mainly. The first one is we haven't used any large amount of data that we have just said in the previous slide. Rather than we have used small amount of data to filter out the correct predictions, teacher, and teaching the correct information to the student model. The second contribution here we have done, that is, we have proposed one novel consensus attentions distillations, which is known as CAD, which extracts the correct teacher's consensus attentions from multiple teachers and reduces the impact of backdoor attentions. And the third one is, in our method, even when the student model is completely poisoned, that means the model is totally like backdoor equipped with backdoor model weight, in the first round, our method can always reduce the backdoor impact to less than 10% after training or convergences. Okay, so these are some of those key highlight of this particular work. So since it is not appeared in the conference so far, so I should not disclose much details. So anyway, so we have developed these CAD mechanisms. With these mechanisms, we have actually achieved some set of results, and also we have performed some experiment and shown that our attack success rate is very less if we adopt our CAD mechanisms compared to other existing works. And we implemented our work under this platform, like Ubuntu, and with having some kind of GPUs, and in i7 computer. So it is mainly done by my master students, implemented by, and it is also tested under different data sets: MNIST, C410, Fashion MNIST, and EMNIST. So these are very widely known data sets, as I know, to test your work and find out those backdoor resistance value, like uh, attack success rate is getting higher or not, or low or not. Low is good, and we receive the low approximately like less than 10%, which is not achieved by other works so far. So we have tested under different datasets, and we found that most of the cases we got the better result compared to other works. Okay, so we are also extending that particular work, that knowledge, like attentions based knowledge distillations technique, and we are extending that works in two different directions. The first one is extending our distillations framework to accommodate such heterogeneity poses and integrating into like these heterogeneous model architectures, which is interesting, but so far we haven't get any result, but yeah, so but we have started. And another future extensions could be like incorporating adaptive, sorry, distillation scheduling mechanisms, which dynamically adjust the influence of each teacher based on their availability, reliability, and contributions, or like contributions quality. Okay, so these are the two directions of this like of this work which we can extend further, and we are in the process of the first part only so far. Okay, so that being said, so we come to the end of this today's talk. So the key takeaways, like the first one is security must be built in, not bolted on. So like AI systems are dynamic, data influenced entities requiring security to be integrated from the very initial designing phase, as traditional security measures are insufficient, as I know, for constantly evolving models, because AI is known as one of the rapidly evolving models, right? So traditional measurements should not be sufficient to protect against AI breaches. Now, forget about the firewalls, because the firewalls nowadays, without having any AI or machine learning techniques, it is solely depends on incoming and outgoing data packet or the traffic. Today, the real battleground is the data. So poisoned training sets can quietly sabotage models, and even like well-trained systems, you can think like it can leak sensitive information if they memorize too much. What does it mean? Because we are actually feeding this data, and if we store those data locally without having any safety mechanisms, it is possible that data theft may come into the picture. So we are entering into a new era where data hygiene is as crucial as the code hygiene. Means code is not vulnerable, however the data is vulnerable. First case. The second case is data is okay, but code is vulnerable. So but we need both are at good level to have some kind of better solutions. If you don't control your data or data pipeline, you don't actually control your AI means your AI systems, right? The third one is very useful. Like it is talking about AI can be both defender as well as attacker. So AI has pros and cons. It can identify hazard as well as like it can actually highlight, or it can give you some alarm even faster than human beings, and as well as it can be used as a weapon. That just I have said, for example, this is a turtle picture, however just change that picture in such a way that machine detects that particular image as one gun, rifle. Okay, so that is very critical. So imagine a bot that observes your security mechanisms and learns how to bypass them. That is also can be the bad side of AI, without explaining why it is actually taking such kind of data. The fourth one is explainability. So you can't secure your AI systems without explaining its actions. If your systems, AI equipped or the machine learning systems, actually cannot explain why it reaches certain decisions, you cannot trust on those kind of results. It's like sealed chamber. Black box models are unknown until they break. So explainability is very much useful. It is required for policy making systems. So explainability is actually, it requires auditing, diagnosis, responding to the dangers, not just a faith. Just this AI model is giving me some kind of response, it doesn't mean that it is trustworthy as long as we don't know their working principles. So your new firewall should be as transparent as possible from the end user's point of view. The next one is massive, like LLM kind of things, like massive language model or large language model. They are strong but fragile. A well-crafted input, possible, it is possible for attacker that highly tweaked data or the input data can hijack the model's behavior, like a phishing email. Or like software engineering, rapid design needs handrail kind of things. It needs some kind of sanitizations before using those input in my original systems. Frequent testing is very much useful before to or prior to testing, or prior to deploy those kind of systems in real environment. The second last is, most teams employ pre-trained model, which is very sensitive aspects. What does it mean? Most of the employees, for example, most of groups, they use pre-trained model, and they may use some third-party data sets. But who knows those data sets, whether those data sets itself are correct or not? What if those sources are compromised? So then we can't answer. So unnoticed biases or backdoors or even some like poison data can enter in my systems through those data sets or through those unchecked pre-trained models. So we must examine our AI supply chain like software dependencies. And the last one is the security is moving target. So here, AI and its threats are keeps on evolving. So today's safe model may be vulnerable tomorrow. Who knows? So continuous monitoring, red teaming, and adaptive defenses are quite necessary while you are talking with those chatbots or automated systems. The monitorings and testings are very much useful. That is what I feel. Okay, so without taking much time, so I come to the end of this talk, and that's the pretty much small discussions about AI securities and their importance. And in this talk also, I briefly, like I tried to discuss about some uh, different types of attacks, for example adversarial attacks or backdoors or something like model theft, like model inversions attack. And also we tried to discuss about some of those solutions mechanisms with the help of federated learning. For example, it is very much useful to preserve the privacy of like a model, like local training model. So however, those federated learning, although it enhances the privacy, but it is still possible some backdoor attack. And those backdoor attack also we tried to show one mechanisms which is known as the distillation process, like attention based knowledge distillation process. And with the help of those process, we can enhance and we can protect against protect better against the backdoor attack. However, in real settings, what we have seen, that is the non-IID data, which not much researchers have addressed. So we tried and we come up with one small solutions which can also work under non-IID settings. And we have also tested that particular CAD, that is consensus based distillations. So that CAD mechanisms also we have tested under different settings, and also we found that the backdoor attack success rates is less than 10%, which is most of other works, which is around 15 to 20%. So we get even lesser than them, like less than 10%. So and so that is one of the works we have done recently. So I happily discuss those things, and that's it. So anyway, so thank you very much for your attentions. I really appreciate it. And if you have any queries, you may contact me. So you can scan the QR code or you can email me. So that would be good, and I'd be happy to answer based on my understanding. Okay, so thank you very much for your presence. So I stop here.
Now it's the time for vote of thanks, sir.
Ma'am,
A very good evening to all. On behalf of the Department of CSE, Cybersecurity, Data Science and AI&DS, VNR-VGIT, I sincerely thank Professor Arjit Karati, Assistant Professor, National Sun Yat-sen University, Taiwan, for his insightful talk on deconstructing the dark side, emerging security risks in AI. Sir, your detailed explanation on key issues such as AI as both defender and attacker, explainability as a security feature, prompt injection, and supply chain risk has truly enhanced our awareness of AI security challenges. Thank you so much, sir.
so thank you so
Thank
much,
you
sir.
very much for having me. Yeah.
Yeah.
Okay. So I share with my email ID because since there are not much time for discussions. So yeah, so if you have any queries related to this work that I have briefly discussed, or anything related to that which comes under my interest, so I'd be happy to answer or try to answer via email. So that will be great. Thank you.
Thank you, sir.
Thank you so much, sir.
Maybe I stop sharing and I may
Sure, sir. Yes, sir. You
yeah,
can leave,
stop
sir.
this
Yes.
presentation. Okay, thank you. Okay, so bye bye, take care, have a nice day.
Thank you so much, sir.
Okay, bye bye.
So just a minute, sir. We'll take a photograph, sir.
I have taken, ma'am. No, I have
Okay.
taken.
Okay, Devasri, madam.
Yes. Hi. Are you able to hear me?
Yes, ma'am. Very good evening, ma'am.
Very good evening.
Good evening, ma'am.
Ma'am, okay, have you taken the photo, ma'am?
Yes, ma'am. Yes, ma'am.
Yeah, yeah. Now we'll be starting the second session. So, a very good evening to all the participants. We are truly honored to welcome now today's second speaker, Dr. Devasri Tripathi, madam, to the day 5 of the AICTE sponsored faculty development program on Joy of AI in Action, applying traditional and agentic AI to real world problems, scheduled to be held online from August 18th to August 23rd, 2025. Dr. Devasri Tripathi is working as an assistant professor in computer science and engineering at Indian Institute of Technology, Bhubaneswar. Her research spans in computer architecture, high performance computing, fault tolerance systems, performance and power efficient designs in accelerators, and machine learning. Her current research focuses on machine learning for systems and system for machine learning. Prior to joining IIT Bhubaneswar, Dr. Tripathi was a postdoctoral fellow in computer science at Harvard University in Harvard Architecture, Circuits and Compilers Group. She is currently working as an associate with Harvard University. She graduated from University of California, Riverside with PhD in computer science. So thank you, ma'am, for joining our today's program. Over to you, madam.
Okay. Thank you so much, ma'am. I'll start my session on AI infrastructure, which is basically primarily the talk will be focusing on how we are optimizing the large language model LLM inference for efficiency and scalability. And I would like the talk to be as interactive as possible. And yeah, I'll pause for questions as we move ahead with the discussion. So now, if we start with the fundamental question, let's say the problem that is given to us is to define what is a cat. In the traditional programming approach, the cat was like, let's say in C or C programming, if we are defining a cat, Then first task for us will be to categorize what are the different features a cat may have, right? Like what is the type of the cat, how many legs it has, what the other features like ears, furs, likes, and etc. etc. Then, as we advanced further with the wave of neural networks, there was supervised learning approach in which the model was given annotated or labeled data. Let's say we give the model a bunch of data for training, and we explicitly mention that this is the picture of a cat, and this is okay. Presentation is not visible. How about now?
Yes, ma'am. It's visible now, ma'am.
Okay, okay. So should I start over again,
Okay.
or I should proceed with this slide?
You can
Okay,
proceed, ma'am, with this slide.
okay. So yeah, with the emergence of the neural networks, we use the supervised learning approach, in which we give our model a bunch of labeled data, and also classify or basically label it as this is image of a cat, and this is not a cat, and so on. And after the model has trained properly, if we give the model an image of a cat in a different posture, it will still be able to correctly classify that this is the picture of a cat. And now, with the emergence of the generative language models like Lambda, PALM, GPT, etc., we like it uses the unsupervised learning approach. So, in the unsupervised learning approach, instead of giving the model the label data, we are basically telling the model that okay, go through this huge pile of books and learn about cats and many other concepts that are present in those books. And once the model is trained using all that information, then when we ask the model what is a cat, it will be defining a cat properly based on whatever it has learned from those books. Okay, so basically, to summarize whatever we discussed so far, like what is a language model? We can define a language model as a subset of deep learning, which takes an input, a prompt or a question as the input, and it produces a text-based response as the output. And whatever intermediate processing happens in the middle is basically the LLM analyzes those input and generates a response based on all its learned patterns. Now, if we test our understanding using a use case, large language model use case, which is basically predicting the next word in the sequence, then let's say the sentence that we have or the fill in the blanks question that we have now is last night I was reading Harry Potter and then we have to fill in the blanks or predict the next word in this sequence. So this is the question that I have for the audience. So if you were forget about large language model or other things, let's say this question was asked to you, then what would be the response that you would give? Like what will be the next word in this sequence? So basically, many of us know that like Harry Potter is a fictional character. There are movies made around the central character of Harry Potter, and there are books written on the specific character. So probably. What we are talking about is last night I was reading Harry Potter, and maybe some character in his books, or like the name of his books where Harry Potter is the central character. So these are the pictures of the books written on the Harry Potter. So the names of the books are Harry Potter and the Sorcerer's Stone, Harry Potter and the Chamber of Secrets, Harry Potter and the Goblet of Fire, etc., etc. So as we can see, there is a common pattern in the way the names are being written for the books have been named. So the pattern is Harry Potter and the, so this is a common pattern. So probably what we want here, or the next predicted word will be name of one of the books. Now the question is, we have about seven pictures in seven books in this picture. So if we are going to predict the next word in the sequence, which book should we refer to? Right. So which book are we going to refer to? And like intuitively, what do you think? Like which book should the model pick up and try to fit in this question? Like where we have to predict the next word in the sequence. So the way humans tend to behave, so any of the seven books, yes, but there has to be some order or some logic, right? Some algorithm based on which the large language models is going to determine it. So let's say if I'm spending too much time with a person, and like I'll try to tell the name of the person, or like I tend to remember things that I have seen more frequently, right? So the model also does the same. Model will rank all these books in the order of occurrence, or like the more frequently the book has occurred in the knowledge base or the database of the model, that specific book it's going to pick and put as the predicted the next word in the sequence. So in this case, if we order the books and try to sort out the probability of occurrence of that specific word after the word Harry Potter then this is the probability of occurrence that we are getting. So intuitively, the one with the maximum or the highest probability of occurrence, we are going to take this word and try to fit it in this sentence. So this is what the large language model also does. So it predicts that the next word in this sequence will be basically philosophers. So the complete sentence now will be: last night I was reading Harry Potter and the Philosopher's Stone. Now there is a catch here. If I modify or twist the question little bit, by adding some context, and the context goes like this, that the additional context is: remember, I live in New York and I bought my book from the United States. Now in this scenario, what will my model predict? So the thing is, like what additional information, or like how is it, how this additional information, or how is this additional context going to change my decision making process? That is what we need to understand. So the thing is, when Harry Potter and the Philosopher's Stone was launched in all around the world, US audience, the publishing house felt that the US audience do not know what the word, like the philosopher word means. They are more acquainted with the word Sorcerer's Stone. So that is the reason, like although in the whole world it was launched as Harry Potter and the Philosopher's Stone, but especially for the United States audience, the book was renamed and launched as Harry Potter and the Sorcerer's Stone. So now, with this additional piece of information, like because I'm saying that I live in New York and bought my book from United States, probably I might not have bought the book which was launched throughout the world except United States. Probably I might have read that the chance of me reading Sorcerer's Stone is much higher than reading this book. So with this additional context, the large language model, what it does, it recalculates all those probabilities and rearranges them in the order of highest probability first. So the Sorcerer's Stone now becomes probability, shows probability of occurrence is 5.1%, and the others are rearranged accordingly. So then the answer that my model is going to return, that is predict the next word in the sequence, will be different. So now it will return sources instead of philosophers, which was what we saw in the previous case. Some key points regarding the AI model. So the Chat GPT or the large language models or any other different Gen AI models, they have huge number of parameters. For example, GPT-3 itself has about 175 billion parameters, and the more the number of parameters, I need a lot of storage space to store them, and I also need a lot of computational resources to basically train my model as well as draw inference from that. And why do I rely on a huge model size, or why do I need so many parameters? Because if my model is large and it has a lot of parameters, then there are more chances that my model will learn better when there are more complex patterns in the data, and it will also behave better for the unseen data, and produce high accuracy results and so on. Second is my inference speed. So if my inference speed is too slow, let's say I'm typing something in the chat GPT, I'm asking a question and then it replies to me after, let's say, 30 minutes. I'll not appreciate that. Like all of us, whoever are using this Gen AI or any kind of resources, we want instant response. That's one of the service level objectives, or the quality of service promised by like all the Gen AI models that we are using. So the inference speed has to be reasonable. It cannot take forever, saying that like I am producing the most accurate output, so I'll take like long time compared to my competitors. That is unacceptable. So that is the reason the models need to will require more computational resources and higher memory, because without that the inference speed will be extremely slow. And that is the reason why we also need to use specialized hardware like accelerators, for example, graphic general purpose graphic processing unit, GPGPUs. Or another example for the specialized hardware can be what Google uses, tensor processing unit, TPUs. So they have built a separate accelerator or a separate chip by which does the AI based computations more effectively in terms of power, like it consumes less energy for the same output, and at the same time it produces instant results. The inference speed is extremely better. And the third point is training time and resources, which means that like the model training these models will be extremely resource intensive, and it will require a lot of computational power, memory as well as time. Because like if we don't use large data set to to train our model, then what will happen is that there is a risk that our model might overfit because of less amount of data used for training. So, any questions so far? Okay. So now the question is, we learned about the language model, fine, but what is large about this language model? Why is it called a large language model? So that is because because it is trained with huge amount of data. It needs lot of computational resources. It needs lot of memory. So the scale, or the basically the scale at which it is growing, or the scale at which it is trained with the data set. So that massive scale basically is termed as large language model. That's the reason we call it large language models. And they rely on the deep learning architecture, which utilizes neural networks, and it uses unsupervised learning, which means we are learning from the raw text data without any explicit need of labeling. So now with the Gen AI application, so the large language models are actually trained to solve some common language problems like text classification, question answering, document summarization, text generation, etc. So I'm sure most of us have used the large language models in our day-to-day lives. Either it can be for question answering. How do I, for example, me, when I before I go to the class, while preparing my slides, I try to look up what are the more relatable examples, what are the different analogies I can use to explain different concepts to the students better in the class. And for the document summarization also, like many of us, if rather than going through it 20 pages document, if I want to summarize it quickly, uh, some people do use the Gen AI interface for that, and it being a language model, it basically nicely summarizes most of the documents. And some of the commonly used examples for large language models are GPT-3, which stands for Generative Pre-trained Transformer 3 model. It was developed by OpenAI. And there are also different other examples for large language models, like Lambda, which stands for Language Model for Dialogue Applications. It was developed by Google. And the third one in this category is BERT, which stands for Bidirectional Encoder Representations from Transformers. It was developed by Google, and there are also several other large language generative AI models that are used in the mainstream. Okay, so to summarize, the main benefits of large language models are its efficiency. It does a very good job in automating the tasks that would have otherwise needed a lot of human effort. Second point is accuracy, that we need to improve the accuracy of tasks like translation and summarization. The third point would be creativity. It helps us generate new innovative ideas. And then the last point will be accessibility. So instead of me going through 10 different papers and then try to gather, I can just ask the chat GPT a specific question. It does a very good job in basically highlighting or giving me some relevant information compared to the basic search engine like Google, Firefox, etc. So it makes the information more accessible for a wider audience. So now that we have appreciated how large language models have affected our lives and what are the challenges for designing different large language models, now let us shed some light on what are the primary driving forces of the computing. We know that large language models consume a lot of computational resources, which means that if you want to reduce the inference time or the response time of the language models, then we need to look at like how to accelerate or how to make the computing more faster. And that is what the crux of my whole presentation today is about. So what we want faster computing, which will also depend on better algorithms, because the better the algorithms, I'll have better, more accurate results. And also the algorithms, for producing good or accurate results, we need more amount of data for training our model. And at the end of the day, what we need is a better value for money. And what happens in the middle is basically the magic box or the topic that I'm going to discuss in the next upcoming slides. So I'm going to pause here for 2 minutes to see if any of you have any questions.
Madam, when you are saying better algorithms, like the algorithms are the same, right? What
Sorry?
is better? When you are saying better algorithms, the
Yeah.
algorithms are the same, right?
So
Like
when I say better algorithms, let's say earlier when we were using different models, let's say RNNs, like we were not able to, the architecture or the model was not able to capture the context for more number of iterations. But with the emergence of the transformer models, for example, we are able to preserve the context for longer iterations or longer amount of time.
That is also one more algorithm.
Yeah.
What is better about it?
So the better is like we are able to store the context for like larger amount of time. Let's say I'm reading a paragraph, and by the time I am talking about the last token or the last word, the model actually forgets about what happened or how I started with this. So that will result in inaccurate or substandard output compared to the transformer models, which are good at maintaining or preserving all those contexts.
Okay, so I feel that is the transformer model, and that is working the way it works.
Yeah.
Encoding, decoding.
Right.
Okay.
Yeah. And second question is, how do we measure the performance of a large language model? So the performance, first of all, from if I am talking about performance from an architect's point of view, so performance we can measure using like latency. Latency means like how sooner, if I am giving some input, how sooner am I going to get the output. Second thing is like what is the amount of data I'm able to process at a given unit of time. So, like first of all, if I am asking ChatGPT a question, right? Let's say I asked a question, it will not give me the answer like instantaneously. It will take some time to produce the first word, or it's going to take some time processing time to produce the first word. So that is something which is one of the metrics of performance. It is called time to the first token. So the time or the duration in which I finished typing my question and the instance in which the model produces the first token is basically time to first token. That is one of the metrics of measuring the performance of large language models. Second metric is after it types the first word, it basically is going to type word by word. So the time between the different words or time between different tokens is also another metric of measuring the large language model performance. So there are actually multiple different metrics. So these are the two important ones.
Like, what is the time, madam, for producing the answer?
What is the time?
Yeah,
Sorry,
in
could you please repeat?
nanoseconds, milliseconds.
Oh, so the time should be in like microseconds actually.
Okay. How many microseconds, madam?
So it depends from model to model. I don't have a specific number in my mind.
Okay.
Yeah, it depends on the size, like the question that I have fed, like what is the size of the question, how many word it comprises of. It's actually proportional to that. Which model I'm using, and how many billion parameters I'm using. So all these are actually factors in deciding how my model is going to perform.
Okay. Like if I had a omni model of
Okay.
5, okay, GPT-5, I had a dash O, that is omni model, and I just give it a simple question: who is the
Okay.
president of India? Then
Mhm.
what should be the response time, madam?
So what should be the? There is no specific thing, right? Like that I can tell you that this is going to be my response time. The response time definitely depends on the model. It's going to depend on the question. It's also going
No,
to
I'm
depend on
I'm
what is
telling
my
you
hardware.
that I'm using the GPT-5 Omni model.
Yeah.
Yeah,
So on
suppose
which hardware are you going to run?
I'll say I'm going to run it on GPUs or TPUs. Then
Okay, so GPUs, TPUs, like depending on which size my GPU is. So all these parameters are basically dependent on deciding the performance of my LLM. So there is no one single number that I have in my mind that okay, this is what I am going like your model is going to perform, or this is the TTFT or TBT your model is going to give you.
can you just tell me the formula, madam, which we use to calculate? You
There
are
is
telling
no single
microsecond.
formula, sir. Like there are researches going on to determine the relationships for that. Like there are a lot of parameters that like there is it's a field of active research. There is no single formula that I can give you.
Thank you, madam.
Yeah. So let's say if like the from a computer architect's point of view, so the limitations and challenges in the large language model optimization are first of all memory constraints and management. So because we need a lot of memory to store the data that is needed for training and inference of the model, so memory and management is plays a very important role. The second thing is the computational complexity and the resource requirements. And the third one that we discussed just now is the latency and the throughput considerations. Another thing is both latency as well as throughput are important. Why? Because latency determines how fast I can get my response, and throughput determines what is the amount of data I am going to process at a given instance of time. The problem, breaking down the problem, is like we have data and compute requirement of the large language models and AI models, and the solution that we are looking for is the data and compute requirement of the large language models can be mitigated by different advancement in the hardware, algorithms, and data sets. So now, so how many of you, how many of you have taught computer architecture in your colleges or departments? I believe like all the audience are faculties in different colleges, right? So computer architecture, which book do you refer to while teaching the subject? So the silence means you have never taught the subject, or you don't recall the name of the book. Okay, so basically, the book that I was taught from at University of California Riverside, where I did my PhD, as well as we also refer to the same book while teaching the class, are both at the UG and PG level. So there are two books. Like one is the Computer Architecture, Organization and Design for UG level course. William Stallings, yeah, William Stallings, and also Hennessy Patterson is the commonly used book for computer architecture classes. And for the PG level course, we use computer architecture and design. So the authors of the book are John Hennessy and David Peterson, who actually won the Turing Award, which is one of the most prestigious award in the area of like engineering world. So they won Turing Award in 2017, and I was actually one of the fortunate people to attend their Turing lecture. So they, for the benefit of the computer architecture community, they repeated their Turing lecture where they highlighted what were their contributions due to which they won the Turing Award in a flagship conference in the computer architecture in 2019. So this slide that I'm projecting is from their Turing Award lecture. So any idea where what are we trying to portray in this slide? So I'll just describe what is the x and y axis. So in the x axis we have different years, and the primary y axis we have nanometers, and in the secondary y axis we have the relative power density per nanometer square. So why is this figure important, and why is he like basically showing this during his Turing award lecture? Why is this slide so important to be discussed? Any ideas or any thoughts? So now government is having a semiconductor mission, like that they're putting a lot of stress on reducing the nanometer technology scaling and things like that, right? So what does it essentially mean, and why is it so important that all like government is trying to reduce the nanometer scaling, basically the technology scaling? Power consumption. So with the lesser nanometer, I'll have more power consumption or less power consumption? With more nanometer, I'll have less power consumption. Yeah, that's right. So basically, what the building blocks of our chips or the circuits are basically the transistors, right? Let's say, let's imagine a situation where like the a big transistor. If I'm using, then I'll have lesser number of transistors in my chip in the same area. But if I'm reducing the number of transistors or reducing the size of the transistors, I can fit in more number of transistors in the exact same chip area, which was basically the Moore's law. And assuming each transistor has similar performance, or it gives similar amount of speed up to my overall circuit design. So the whole target was, can I reduce the size of my single transistor or my basic building block of my chip, so that I can, in the same chip area, I can fit in more and more amount of transistors. But the thing is, transistor function, that's great, but it also dissipates the power in terms of heat. So that when the size of the transistor went down, the power density, which was also governed by the Dennett scaling, actually increased by significant rate. So this is the trade-off figure that like every processor company or every computer architect in the world is more concerned about. So if I can reduce the size of the transistor, fine, but at what cost? My power is actually going up. So there actually happens a situation when, let's say, I have put so many hot transistors in a small chip area. What will happen is that if one transistor is becoming too hot, all the neighboring transistors or the neighboring components have an inductive effect and they get heated up as well. And lot of if the circuit gets heated up, then it's going to become unreliable, so it's going to give wrong results for the same computation. And this is the like this figure shows the trajectory of the processor performance from 1980 to 2020 and so on. So if we begin with earlier, we were having CISC. So CISC are basically all the laptops having x86 architecture are basically CISC, which was complete instruction set computer, which means that we had lesser number of instructions to process, but each instruction was complicated, which means it was doing two or three operations at a given point of time. And the reason why John Hennessy and David Peterson actually got the Turing Award was because of this green part. This was the era, or this was their main contribution, which got them the Turing Award. The ARM processors, that is like in your phones or any of the edge devices, iPads, tablets, etc., are basically based off of RISC architecture. So they have more number of instructions, but all the instructions are too simplified to be processed. And because of this, because of the RISC processors, the many of the processor company actually thrived, and the number in the bracket here shows the processor performance per year. So in the CISC, the processor performance per year was about 22%, and for the RISC it was huge. It was like the processor performance increased by 52% per year. So the thing is, why is this processor performance is important? Why are we focusing on increasing the performance of the processor year by year? Look, if you are going to buy a laptop in the market, and the seller tells you that this laptop which is launched this year performs exactly the same as the laptop that performed 3 years back, then you'll simply come back from the market without buying anything. You'll say that, okay, my old laptop is good enough. There is nothing that I'm going to gain. Then why will I spend more money? And what's the reason I'll get a new laptop or a new processor, basically? So for the semiconductor or the processor companies to thrive, they have to show better performance each year, so that from the business point of view, it's beneficial for them. And all this actually happened because of Moore's law that we were talking about. The transistor size was decreasing. So, like the main idea was the number of transistors in the dense integrated circuit was actually doubling approximately every 2 years. And this was actually pitched in a paper written by Gordon Moore, and the Moore's law is coming from the name of the scientist Gordon Moore. The paper appeared in 1965, and it was actually validated over like almost 50 years, like half a century. And the law was actually used by the semiconductor industry for planning and to set targets for research and development, and basically make a lot of business out of it. And this plot was basically Moore's law, that my transistor size is actually reducing and the number of transistor actually is increasing. And the blue line here was basically the Dennard scaling. So what Dennard scaling stated was that even though the number of transistors is increasing, don't worry too much about the power, because the power is going to increase at a proportional rate. So nothing to worry about. So that is the statement that in the Dennard scaling, Robert H. Dennard, a researcher from IBM, stated. And so it allowed the CPU manufacturers to increase the clock frequency from one generation to other generation without significantly affecting the power consumption or the overall circuit's power consumption. So this is fine, but there was an era like around 2005 time frame when increasing the frequency was not giving better performance. Like, let's say I am in a situation where I have invited about 50 guests to my home, and I have to, let's say, make biryani, and I have just one stove and it's already at the full flame. So how am I supposed to make food for 50 people in one stove, and it's not that, like, the it's already in the full flame, full potential, and I have barely some 1 hour before the guests start coming in. So this is kind of a crisis situation. And can you offer me some solution to handle this kind of scenario? Anybody from the audience? I have to make food for 50 people. The question is, I have to make food for 50 people in 1 hour, and I have just one single burner stove, and the stove is already at the running at the full potential, but there is no way practically I can make or cook food for 50 people in 1 hour with just that stove. So how do I manage the situation? And please do not tell me that I'll order from outside, I'll use Swiggy, Zomato, it will cost a lot of money, and I don't have so much budget for the party. So what do I do? Swiggy and Zomato is not an option. Any other solution you can provide? Yeah, borrow stove from the neighbor, right? So that is exactly what I'm going to do. So I'll knock every neighbor's door and request for a stove, and I'm going to put all the stove in parallel, divide my food into multiple different containers, and start cooking parallelly, right? So that is one of the way I can finish the target or reach my target before the hungry guests come in for food. So that is exactly how the multi-core processor also work. We take the data, divide it, and run it parallelly on multiple different processor, assuming that we will try to get better performance, because the single processor performance is not giving me better results. So now I'll have multiple different, like multiple number of similar kind of processor. I'm going to divide the data and work parallel through it. So basically, but there is some theoretical limit to how much I can gain. Let's say for, let's say, cooking biryani, I borrowed 1,000 stoves, let's say. So does it mean that my overall cooking time will reduce by 1,000 times compared to if I had to basically cook using one stove? let's say my for cooking using one stove, I was supposed to consume, let's say, 6 hours of time. But now that I have 1,000 extra stoves that I borrowed from my neighbor, will this time reduce by 1,000 times? Yes or no? What do you think?
No, no, ma'am.
Why not?
Because we can't cook that much of food in small amounts of time.
Yeah, so basically the reason being there was also some part which was sequential. Let's say me getting the groceries from the market or chopping the vegetables or soaking the rice. So it was me doing all of the things, which was a sequential process. So even though I have parallel stoves, yes, but that part will still take its own sweet time, right? Which was sequential. It was I couldn't parallel. I cannot parallelize it. I'm the single person. I have two hands. I cannot cut vegetables that I can put or ingredients that I can put into 1,000 containers. So yeah, practically it's not possible. So that's the reason. So that is what the Amdahl's law tells. It gives us a theoretical maximum limit of like, will it be beneficial for me if I try to buy or get in more number of processors or multi-core processors and try to parallelize it? Will it give me the best performance or not? So now the thing is, we can see that like it has almost hit a bottleneck or a saturation point. So is it the dead end? Is it the end of the line? Are we going to see processes with better performance, or that is it? So this is what the question that they asked us, the audience. This was actually answered by them in the next slide, which was now, like, instead of thinking or trying to focus on increasing the performance of a single processor, better to design custom processors or domain specific processors, like, which will try to get best performance at the minimum energy consumption. So whenever we hear about this word large language model, yes, we are concerned about the performance, but cannot ignore the energy efficiency aspect of it. So, by domain, we mean like anything from autonomous vehicles to, let's say, AR, VR, augmented reality, virtual reality, anything can be specified as a domain. So, a bunch of applications having similar functionality can be classified as a domain of um, applications. And the examples of the domain specific architectures are GPUs, neural network processors, and NPUs, TPUs, let's say, by Google, and so on. So this is something that we should spend and invest our time and energy on if we want to still get better performance. If you want this trajectory to continue, so this is what we should focus on. That was their advice to the research architecture or the computer architecture community. So I'll pause here for about 5 to 10 minutes and see if we have any question, and we will resume the talk at like 8:25. I'm happy to answer any questions if you may have.
Ma'am, one of our participant is asking like, how can we develop custom LLM?
How can we develop? So you mean custom accelerator or custom LLM?
Custom
LLM.
LLM he is asking.
Yeah, LLM, I have no idea. I never tried to develop any custom LLM. So my area is in computer, area of expertise is computer architecture. So I take the LLM, which is like the generic ones, and try to design my custom accelerators best suited for that.
Okay, please tell about accelerator, madam. Custom accelerator.
How do we develop custom accelerators?
Yes.
Yeah, so yeah, I think the rest of the talk is actually focusing on that. So we try to find out which, let's say I have different parts of my processor, which is the bottleneck part if I'm running a specific large language model. So first is we identify that aspect and try to, let's say my bottleneck is, let's say, memory. So I try to increase my memory size in the custom accelerator that I'm designing. Or if my bottleneck is the processors, so then I try to increase the number of processor or which part in the processor is the bottleneck. So identifying what is the bottleneck and working on that, that is basically the process of developing the custom accelerators. Keeping
Thank you.
into mind the performance versus the energy trade-off aspect.
Thank you.
Okay, so welcome back to the talk. Uh, do you have any questions for me, or we should proceed?
Please go ahead.
Okay. So, let's shed some light on how has the deep learning hardware evolved over the years. So, if we take a look at the scalability or the complexity of the deep learning models, that has actually dramatically increased over the time or over the years. So, the complexity of the natural language processing models, for example, has increased about almost 1,000 times in only 2 years from BERT, which was launched in 2018, to GPT-3 in 2020. But the ability to train successively more complex model has been dependent on increasing the hardware's performance. So, like on the x-axis, we have the years, and on the y-axis, we have the peta floating point operations per second, which is a measure of the throughput multiplied by days of training. So earlier, as we can see, the scalability of the model was not that great. So from AlexNet to ResNet, like till 2016, like the model scalability was not that high. But after 2017, when the transformers was actually introduced in the paper All You Need Is Attention by Google Brain, um, where they introduced the transformer networks, all the models based on that started scaling up like anything. So this figure actually shows how a single GPU performance has scaled up to meet the demands of the deep learning. And on the x-axis we have the years, and on the y-axis we have integer 8 tera operations per second. So the GPU inference performance has actually improved by 317 times, which is more than doubling every year. So if we take a look from 2012 to 2020, so in 2012, so these are the numbers or the letters here basically show which architecture in the GPU. So in 2012 we had Kepler architecture, and the numbers are for this specific model. And 2015 we had Maxwell architecture, 2016 Pascal, 2017 Volta, Turing, and Ampere, and so on. So the mechanism or the pattern that like the GPU inference performance is increasing more than doubling every year is basically now called as Huang's law. And increase is due to adding of some specific data types, specific instructions, and many different aspects. So one of them, like for example, there was a 3 times speed up from 2015 to 2016 from Maxwell to Pascal. That was because first NVLink, where we have multiple GPUs, because the data is so huge, and GPU memory can be maximum, let's say 84 GB or maximum within 100 GB. So it's not possible for us to fit all the data in a single GPU memory. So we divide the data and all the GPUs compute parallelly. So the bottleneck can be inter-GPU communication. So NVLink actually increased the performance by about 3x. Similarly, the performance increased by about 5x by the emergence of the NV switch, as well as the tensor core architectures. I'm not going to discuss what each of these contributed, but just shed some light on what were the trends, or how has the deep learning architecture or hardware evolved over the years. And then there was again a 2x speed up because of addition of integer tensor cores. And then finally, in Ampere, we see a huge speed up because of tensor core support for sparse data computation. So all the deep learning like layers, we can visualize that as sparse matrices. So the algorithm for sparse matrix and algorithm for dense matrix are completely different. So having a specialized hardware or tensor core support for doing this sparse data computation actually led to massive speed up. So to summarize, there are a lot of components in accelerating the deep learning on the GPUs. Some are hardware advancements, some are software advancements. Hardware and advancements we discussed in the previous slide, like NVLink, which connects the GPUs, NVSwitch, connecting cluster of GPUs together, and different data types from floating point, FP16 to integer 8, and so on, and having some specialized cores. And there were also a lot of software advancements in this domain, like introduction of CUDA deep neural network, UDNN libraries, or the C, like all the different libraries by the CUDA or the NVIDIA group. And there were also different training pipelines, different library support that was developed, which all helped or aided in accelerating the different deep learning models on the GPUs. So here now we will discuss regarding what are the different layers or stacks.
Ma'am,
Which are
here I have a small question, ma'am.
sure, sure.
Why is a GPU more efficient than a CPU for training large language models, ma'am? And how does its architecture make it suitable for deep learning?
Okay. So just give me 1 second. I have a nice slide for you. I'll just dig it up and I'll show it to you so that it's easier to visualize, and then I'll discuss that. Just 1 second.
Okay, ma'am, sure.
Let me look it up. Okay, yeah, I found it. Is my slide visible?
Yes, ma'am.
Okay.
Yes, ma'am, it is
Um,
visible.
okay, great. So let's say in this example, I am commuting from home to work, and I have two options to go from my home to my work. And one is I'll take in my Ferrari, which will have two seats, and I'll reach in, let's say, 20 minutes from my home to office. And the second option is I'll take a bus, which will, let's say, have 100 seats, but it will take me 40 minutes to start from home and reach at the work, because it's going to stop at multiple places and wait for the people to get in and get off, right? So out of these two options, which option would you prefer for commuting from home to office? Car, two seats, 20 minutes, or bus, 100 seats, 40 minutes?
Obviously, car.
Okay, well, the answer actually depends on what is my objective. If my objective is to deliver a remote session, then I'll go with a Ferrari so that I can reach sooner. I can set up my laptop and then I can get started with the online discussion. But if the objective is to deliver a in-person talk, I cannot just reach earlier and then just sit there waiting. And if I use the car for transferring all my students or all my audience, let's say, then it will take forever, right? So it will be basically 50 trips multiplied by 20 minutes each one way. So in that case, bus will be more preferred, because my objective is I need the students or the audience also to reach with me so that we can get started with the session as soon as possible. This is remote talk. This is in-person talk. So for remote talk, this one is a better option. For the in-person talk, this is a better option. Okay. Or do you have any other solutions? Okay. So in this example, the car is actually the CPU. So that is what the CPU does. CPU is good at handling less amount of data, but it gives us like very high or very low latency. Low latency here is the time taken when I start here and when I reach here. So that was 20 minutes. So latency is 20 minutes for the CPU, which is low, but the throughput is how many data items I'm processing at a given point of time, which is analogous to the number of passengers or the number of seats that I have. So here the throughput was 2, but the bus is actually a GPU. So in like in the bus, it's little bit slower because many people are getting on and getting off at random points. So like the latency is about 40 minutes, but the throughput is significantly high compared to the CPU. So it was almost 50 times higher. So this is the GPUs or the accelerators are more commonly used in large language models or deep AI models because we are dealing with huge amount of data. Like yes, we are concerned with the latency as well. We are concerned with the speed as well, but the amount of data that we are processing per unit time is also very important, and that is the reason accelerators are becoming increasingly more popular for handling the like large language models. And now, answering your second question, that what specifically changes between a CPU and GPU, which helps it behave like better when it comes to large language models, or in like for that matter, any AI or model which needs huge data to for processing. So actually, CPU and GPU are designed very differently, and this slide I'm showing so that the difference we can visualize pictorially and develop a mental model for what the differences are. The point number one or the difference number one is the cache memory. So the CPUs have a huge cache, GPUs have a small cache. So if I have, intuitively speaking, if I have a huge cache, then my latency will automatically reduce. So that is the reason the CPUs have low latency because of this cache, and GPUs because I have so many threads and all the threads are working on different data items, then there are chances that each thread is going to throw each other's data out of the cache. So it does not make sense for us to invest in a huge cache. The GPUs have a very small cache compared to the CPUs. Second point of difference is the registers. The second point of difference is the registers. So here the CPUs have huge register compared to the SIMD, and the SIMD unit are basically the ALU units because they have a lot of parallel threads. Each thread will be using some functional unit or the ALUs to do their computation. So ALUs are like stops we can think of. So here we need lot of stops because we have a lot of parallel threads that are going to work, which is less in size compared to the what we saw in the GPUs. And the third part or the main point of difference is the CPUs have bigger control logic and GPUs don't have control logic, rather they have thread management logic because we are dealing with parallel threads. So if I discuss one by one, so first feature in the CPUs is they are more latency oriented devices. We look at low latency when we are using CPUs. So that is because we have powerful ALUs that help reduce the operation latency. Second thing is that they have huge or large cache that helps to reduce, like if the cache size is huge, then there is no need to access the DRAM or the memory. So everything is cached here so that the access latency is less. And the third thing is that all this is managed using a sophisticated control mechanism. In the architecture class, like we have learned about branch prediction, data forwarding, all these things, which help us reduce or increase the performance, reduce the latency and increase the processor performance. So that is what the role of the control unit is. On the contrary, the GPUs have actually smaller caches and they don't have any branch prediction or anything like that. So that's the reason they don't have control mechanism. And because they reduce the size of the cache, they reduce the size of the control mechanism. So this extra space that they saved by reducing these two, they have now used it or dedicated towards development of the ALU units. so which is heavily pipelined, so that we can fully utilize all the parallel threads or parallel resources and tolerate the latencies as much as possible. But because of this parallel threads, we are having a huge throughput. So yeah, basically that's the difference between CPU and GPU, and that is the reason why large language models or basically big data processing is relying more on the CPUs compared to the GPUs. Did I answer your questions, ma'am?
Yes, ma'am.
Okay. So back to our original discussion. Okay. So in the large language model, we have the application or the workload. Then we have a training framework, and the next thing is, like I said, the GPU cannot, like a single GPU cannot fit in all the data that the large language model needs. So we divide it among multiple GPUs. So, and this GPU are going to, let's say I have a huge matrix of 10,000 size, and each GPU can handle maximum 100 cross 100. So I'm going to divide it like among them, and they have to communicate with each other and synchronize with each other. So that is basically the collective communication, and we have a CPU GPU server. Okay, another thing in mind is that the GPUs cannot exist by themselves without the help of a CPU. They are slave devices. GPUs do not have any operating system, they are slave devices. They need to be connected with the CPU, which is the master device. Master device tells that this GPU is going to deal with data A, let's say, this GPU is going to deal with data B, and so on. So it's the decision maker or the master in this cluster is the CPU. So every GPU cluster must have a CPU which connects them together, which divides the data and the application among the GPU. So this actually block diagram is what setup that I have in my research laboratory. So we have a server with 8 GPUs, and 4 GPUs are actually present in one node connected to a CPU. This is node 1, node 2, and both the nodes are connected to each other using network interface card. So that is the reason inside GPU computation is important. We have to make it faster. And second thing is that if the computation is faster but this connection, the communication channel is slow, that will also kill the performance. So we have to make sure that the communication channel is also as fast as possible. So all these aspects play a role in increasing the performance, overall performance of the large language model. Okay, and this slide basically I have taken data from all the different generations of the GPUs starting from 2010 to 2024, which technology scaling or which node they have been built on. So they have initial one from 2010 was built on 40 nanometer technology node, and in 2024 we have Blackwell, which is built on 4 nanometer technology node. And the blue part is the good part, that the performance in tera floating point operations per second. So this is a metric of throughput. So as we see the GPU, we typically tend to measure the performance in terms of throughput, because they are all throughput oriented devices. So from one generation to another generation, the performance or the throughput has increased. But the concerning part is the orange line, which basically tells that the power consumption of all this generation of the GPUs have also increased significantly. So the main takeaway from this slide or the discussion so far was the GPUs are good in handling the large language models, but they have some problems that they suffer from performance and energy challenges. So the introduction of transformer was done by Ashish Vashwani in Google Brain through their MIPS 2017 paper named as "Attention is All You Need." So the introduction of the transformers and their outstanding performance for conducting all the natural language NLP tasks have driven the rapid advancements in AI. and all the major tech companies such as Google, OpenAI have invested billions and billions of dollars in trying to increase the model and make them more powerful. And this trend is actually going to increase more and more. But the issue is behind the scene or behind these AI services like chatbot, we have the data center which is equipped with a lot of GPUs, and using these GPUs is actually creates a huge demand for power, and this has led to a lot of carbon emission. So recently, I had been to Microsoft Research Bangalore for their academic summit, and one of their main driving factors or major concerns is like there are. So Microsoft Research is actually in Bangalore is one of the leading teams in the area of LLM architecture or LLM infrastructure development, and one of their major thrust force is also sustainable AI, or how to reduce the carbon footprint, how to reduce the energy consumed by the large language models without affecting the performance of the large language model significantly. So the whole question or the whole discussion that the community is now trying to answer is, can we reduce the power and energy used in these large language models? So yeah, here as we discussed, the computation actually happens within the GPU. Communication happens across the GPU. Both of them are important for the performance of the large language models. And there are some traditional in power management techniques that I have been and my group has been working on. So I'll skip this slide in interest of time. So the main question that we are trying to have an answer to is, how do we minimize the power usage of the AI? Like, and second thing is like, which one is the most energy hungry part? Like, is training the most energy hungry one, or fine tuning, or inference? And second thing is like, is the computation taking more energy, or is communication taking more energy? So to answer that question, in one of the recent research papers from the group, we were looking at the large language model training aspect. So this is the trace file that we are generated from a single GPU. So the trace file, what it shows is it has two phases. One is the forward backward pass that resembles the compute phase, which happens within a single GPU, and the parameter synchronization phase, which is basically resembling the communication or all reduce kind of behavior, which happens among different GPUs. So and then we try to basically show and profile the data and show which one takes how much time as a breakdown. So for different models of the GPU, this shows the breakdown of the communication time shown in blue, the computation time shown in pink, and the idle time shown in green color. So here we can see that for the, let's say for the micro llama, almost 64% of the time is taken in the communication, the green phase, sorry, the blue phase, the blue color. So one of the important findings that we showed in our paper was, in the real GPU, like in the real application, while it's running on the GPU, we are seeing that the frequency is increasing at the communication phase. So intuitively, during computation, you need high frequency. In the communication, you don't need that much high frequency, but the GPU was, or the in the real world, it was performing the opposite. So this was actually, the red line was showing the frequency which is shooting up during the communication time. The shaded portion in green shows the communication time. So the solution that we provided was, we forced the frequency to go down during the communication time using some APIs that NVIDIA provides to be publicly used. And by doing that, we forced the red line or the frequency to go down, and because of this, we saw that we were able to save the GPU energy by almost on an average 17%, and the overhead in the training time increased by 1 to 2%, which is not that significant compared to the energy saving that we observed in this kind of scenario. So, any questions so far?
Madam, there is a question asked by Virabhadra sir.
Oh, please tell about the programming used in the GPU or to communicate with GPU. So GPUs, the programming language that initially we use is the low-level language is CUDA programming. It's a C-like programming language. But currently for large language model training, we have the Python libraries available for that. So the backend is still the CUDA program which GPU understands, but we have a wrapper or the Python libraries for that. The TensorFlow and PyTorch libraries can be used for programming the GPUs. And for the communication, we have something called as collective communication library. Yeah, this slide. The collective communication. So NVIDIA has its collective communication library, NCCL, and we tried to improvise on that, and that was the main idea of the PCCL paper. So yeah, that is the two ways to program the GPU. Either we can write this CUDA program directly, or we can use Python libraries to work on them.
Ma'am, I have a question, ma'am.
Sure.
Suppose I typed a query or I have posed a question to LLM. So
Mhm.
which is going to be processed, ma'am, either GPU or CPU?
So if we are typing a query in the uh, like in the large language models, so first of all, when you are saying you typed a query, I'm assuming you are using a cloud based system, right?
Yes, ma'am.
Yeah, because like the large language model can be processed in a CPU as well as GPU. So the like when we are in my experiments, like there are all different options. I can do 100% the in this thing, like the whole computation can be done here. The whole computation can be done on the GPU. Half is also possible, but typically in the cloud system, the CPU actually passes on, and all the computation actually happens in the GPU itself. Once the result is ready, the CPU basically tells these are the results of the computation.
Is this a CPU GPU combination is must, ma'am? Can't we
Yes.
perform only with CPUs or GPUs is not possible?
Only CPUs, yes, it's possible, but it's not that efficient because we are dealing with large amount of data. So that is the reason we take GPUs as well as accelerators or add-on devices. Only GPUs not possible. GPUs cannot exist alone without the help of CPU because they are slave devices. They don't have any operating system or anything. So CPU has to be associated with a GPU.
Okay, ma'am. Thank you so much.
Any other questions by the participants?
Oh, so to answer your question, ma'am, I had this slide from my PhD time. So like when an application is given, what CPU does, it takes the application, it breaks it down into different kernels. We can think of, let's say, the neural networks. We have a convolution layer, pooling layer, and all these layers. We can visualize them as different kernels. The kernel will have different blocks of data. So these like blocks, the yellow ones have, let's say, add a plus b. So addition is this common thing, but like a plus b, like the data, like we have different some, let's say, 1 million data points. All of the data points we are doing addition. So what will happen is that like this is being divided among different processors in a GPU. So GPU will have some 20-30 processors running in parallel. Actually, each of them are multiprocessors. SM stands for streaming multiprocessors. So this chunk or this block is being mapped to different resources so that they can start executing parallelly. So if CPU is not in the picture, there is no one to tell the GPU which kernel they have to work on, which kernel is working, like constitutes of what data and so on. So each GPU must be associated with a CPU to basically do all that, like a master device to take all that decision. Okay, so if there are no more questions, I think we can end the session here.
Okay, ma'am. Darshi, ma'am, could you please switch on your camera for one photograph, ma'am?
Sure. I don't see myself. Yeah.
Thank you, ma'am.
Thank you so much, madam, for joining our today's session.
Thanks, Rasmita ma'am.
Now it's the time for vote of thanks. A very good evening to all. On behalf of the Department of CSE Cybersecurity Data Science, AI&DS, VNR-VJIT, I extend our sincere gratitude to Professor Devashri Tripathi, Assistant Professor, IIT Bhubaneswar, for today's insightful session on real-world use cases of traditional and agentic AI. Ma'am, your clear walkthrough of next word prediction and NLP LLMs in workflows problems. Connect theory to deployment realities. I also thank all participants for your active engagement and thoughtful questions. Thank you so much, ma'am.
Thank you.
Thank you, ma'am, for joining the session. Thank you so much. Good night, madam.
Take leave. Good night.
Good night, ma'am. Thank you.
So, dear participants, tomorrow is our last day. Kindly please attend all the tomorrow session.
Dear participants, feel free to respond here. Participants, if possible, could you please switch on your
You
cameras?
can switch on your video for some time, for 2 minutes like that. You can participate for tomorrow's event. Tomorrow we have valedictory session at 6:30 to 7:30 p.m. So kindly please interact with our speakers.
Thank you so much.
If any question or anything are there, kindly ask to our speakers. So thank you all. Good night. Kindly attend tomorrow's event program. Tomorrow's program. Thank you all.
Thank you all. Thank you.